In this video, we're going to talk about the properties of liquids and the intermolecular forces. The learning competency for this video is to describe the following properties of liquids and explain the effect of IMF on these properties, and to explain the properties of water with its molecular structure and the intermolecular forces. So let's start with this figure. As you can see, there is a needle floating on water. Now the question is, how? Some would say it's because the needle is light, that's why it floats. Actually, it's not. If you drop the needle vertically, it will sink. So what is the reason? This is due to the surface tension. Surface tension is the measure of the elastic force in the surface of a liquid, meaning it is the amount of energy required to stretch or increase the surface of a liquid by a unit area. Now let's have a closer view of this diagram. Molecules at the top or at the surface of a liquid are only pulled inside by other molecules, specifically below them. So remember in physics, if you have a downward force or a downward pull, you always have an upward pull. Okay, so to have a balanced force. Here, there is no upward pull to balance the downward pull. This results in a net pull inward on surface molecules, which causes the surface to act like a skin covering the liquid. And then it tends to shape the liquid to have the smallest possible surface area, which in a form of a sphere. Compared to the surface molecules, the molecules in the middle are attracted in all directions, as you can see in this figure, right? So the intermolecular forces at the surface tend to pull the molecules into the liquid and cause the surface to tighten like an elastic film or skin. Okay, so you have to remember that liquids that have strong IMF also have high surface tension like water. Okay, so that's one of the relationship between the IMF and the property of a liquid. So high IMF, high surface tension. Water has high surface tension as a result of hydrogen bonds. So this figure is what we call beading. So beading happens when a polar substance is placed on a non-polar substance. For example, when cleaning something, a car, okay? So you use soaps or detergents, right? So why? How do they clean the surface? Soaps and detergents are called surfactants. So they disrupt the hydrogen bonding at the surface of a water. This increases the ability of water to wet other substances. Okay, so likewise, surface tension decreases as the intermolecular forces weaken. So it's like a direct relationship. Before we go to the next property, let me introduce you to this concept, the cohesive and adhesive forces. So just to give you an overview, cohesive forces are forces between the molecules in the liquid. Adhesive forces, on the other hand, are forces between the molecules and the surface of another substance. So you can see here in the diagram, in the left side, the water molecules interacts with the glass wall. Okay, so this creates an adhesive force. Okay, so the water molecules interact with another molecule. This will now be called as cohesive forces. Now, if adhesive forces are greater than cohesive forces, you will form a concave, like here in water. This is because water molecules adhere to the wall more than to each other. Now, if cohesive forces are greater than adhesive forces, like here in mercury, you will form a convex. So this is because the mercury atoms at the surface adhere to the wall less than to each other. Okay? So in the laboratory, you call this a meniscus formation. Okay? So when you are reading clear solution, clear colored solution, you have to read the lower meniscus. Okay? Now, if you are reading a heterogeneous solution, you have to read the upper meniscus. Now, the rise of liquids up narrow tubes is what we call the capillary action. Okay, so this results from the competition between attractive forces between the liquid molecules, or the cohesive forces, and the forces between the liquid molecules and the walls of the glass, or adhesive forces. So capillary action is also called as capillarity. It is shown by water rising spontaneously in capillary tubes. Okay, so you have to remember a thin film of water adheres to the wall of the glass tube as water molecules are attracted to atoms making up the glass. Okay, glasses are made up of silicon dioxide, right? So as you can see here in this figure, the wider the tube, the less the water molecules adhere to the wall. But here, as you narrow it, the water rises up. Okay, another example is this one. So when a doctor takes blood sample from patient's finger. So remember that the surface tension causes the film of water to contract and pulls the water up the tube. So surface tension and capillary action go together. We also have viscosity. Viscosity is the measure of a liquid's resistance to flowing. Thus, a higher value means it has more resistance and therefore flows more slowly. So viscosity is related to the ease with which individual molecules move around in the liquid, and thus to the intermolecular forces. Okay, so take note that viscosity increases with stronger intermolecular forces and decreasing temperature. So IMF and viscosity direct relationship, viscosity and temperature indirect or inverse relationship. Okay, so viscosity is measured in units of poise. So the SI unit for poise is Pascal second or Newton second per meter squared. So you might encounter in some books the unit Stokes. Okay, Stokes and poise are both units of measure relating to fluid viscosity. Remember, viscosity is typically defined in two forms: the dynamic viscosity and the kinematic viscosity. Dynamic viscosity is commonly measured in poise, while kinematic viscosity is commonly measured in Stokes. This table shows the viscosities of a series of hydrocarbons. We have hexane, heptane, octane, nonane, and decane. If you notice, as you increase the number of carbon atoms, the viscosities increase, right? Because you have bigger or longer molecule, so you have higher surface area, thus increasing the IMF. And again, IMF is directly proportional to viscosity, so higher viscosity. This table shows the viscosities of liquids of some pure substances. Here you have water. Water has a viscosity of 1 centipoise or 0.001 Pascal second. Okay, so substances composed of small nonpolar molecules such as carbon tetrachloride and benzene have low viscosities because again, nonpolar substances only have London dispersion forces, right? And London dispersion forces are one of the weakest attractive forces. Now, what I want you to focus on is glycerol. Glycerol has resistance to flow of more than 1,000 times greater than water. So the question is, why? Given the molecular structures of water and glycerol, we can tell why glycerol has a higher viscosity than water. So glycerol has high viscosity due to the three hydrogen bonding sites. So remember, the larger number of OH groups allow glycerol to form more hydrogen bonding with other glycerol molecules. So it makes the intermolecular forces of glycerol stronger than those of water, and its resistance to flow greater. And of course, the molecular shape. Since glycerol is a larger molecule, this will have higher IMF. therefore higher viscosity. Okay? Next, we have the vapor pressure of liquids. The water molecules in the liquid evaporate and go to the vapor phase through a process called evaporation or vaporization. Now, there is a difference between the two, but in this sense, it can be used alternately. So remember, a vapor is the gas phase above a substance that exists as solid or liquid at 25 degrees Celsius and 1 atmosphere. As you all know, gas molecules move in random directions, then collide with other gas particles and the walls of the container. Now, some will strike the liquid surface and condense back into it. In the open flask, some of the water molecules in the vapor phase find their way out and are lost to the atmosphere. In a closed container, none of the gas particles are able to get out of the container, and eventually, the number of molecules that go into the gaseous state would equal the number of molecules that condense back. So when the rate of condensation of gas becomes equal to the rate of evaporation of the liquid, the gas in the container is said to be in equilibrium with the liquid. Now, when equilibrium is reached, no more net change occurs. But remember, the molecules are still changing phases, but there is no net change. The change is not seen because the rate is equal. Okay? Specifically, we call this dynamic equilibrium. Another point to remember is that vapor pressure is independent of volume of the container as long as some liquid is present. This is now what we call a liquid vapor equilibrium. Okay. Now, like any gas sample, the molecules in the gaseous state over its liquid state create pressure. Okay. And of course, the greater the number of gaseous particles, the greater the pressure exerted by the gas. So this is one of the relationships between variables that describe a gas. Okay, if you remember from our previous video. Now, the pressure exerted by gas in equilibrium with the liquid in a closed container at a given temperature is called equilibrium vapor pressure, or simply vapor pressure. Okay, to make it simpler, equilibrium vapor pressure is the maximum vapor pressure of a liquid at a given temperature and that it is constant at a constant temperature. With that, you have to remember that it increases with temperature. So this graph shows the vapor pressure of water versus temperature. When temperature is high, more molecules have enough energy to escape from the liquid. At lower temperature, fewer molecules have sufficient energy to escape from the liquid. This is because more molecules have enough kinetic energy to overcome the intermolecular forces. Now, what is the relationship between vapor pressure and the intermolecular forces? Vapor pressure depends upon the nature of the liquid and consequently on the intermolecular forces. Okay, so remember liquids with high vapor pressure, we call them volatile liquids or volatiles. They evaporate quickly and have weaker IMF. Now, liquids with low vapor pressure, they have strong London dispersion forces and strong dipole-dipole forces. As you can see in the graph here, at higher temperature, more molecules have enough energy, therefore they have higher vapor pressure. Okay, so let's discuss this more. Okay, so consider the vapor pressures of the following substances. Ethyl alcohol and water have very low vapor pressures. Both liquids have the strong dipole-dipole interaction called hydrogen bonding. Okay, acetone here is polar but does not have H bonding, so its vapor pressure is of intermediate value. Now, pentane is a nonpolar substance and its vapor pressure is high compared to those of water and ethyl alcohol. Okay, so I hope you can see the pattern. Okay, so you have to remember when liquids evaporate, the molecules have to have sufficient energy to break the attractive forces that hold them in the liquid state. So the stronger these intermolecular forces are, the greater amount of energy needed to break them. Now, for some substances with weak intermolecular forces, the energy requirement is easily obtained from collisions with other molecules and absorption of energy from the surroundings. So that's why many molecules can vaporize, resulting in a high vapor pressure. But for molecules with strong intermolecular forces, gathering enough energy may not be as easy and therefore register low vapor pressures. Okay, so with that, the stronger the intermolecular forces are, the lower the vapor pressure of a liquid is. So again, this is another relationship. Vapor pressure is indirectly proportional to IMF. Now, the relationship between vapor pressure and strength of intermolecular forces is consistent with the trends in two other properties of liquids: the enthalpy or molar heat of vaporization and the boiling point of the liquid. Okay, so let's have first the molar heat of vaporization. So the symbol for molar heat of vaporization is this one: triangle, letter H, and subscript VAP for vaporization. Okay, so this is the energy required to vaporize 1 mole of a liquid at a given temperature. So this table shows the molar heats of vaporization and boiling points of selected substances. So remember, the heat of vaporization may be considered a measure of the strength of intermolecular forces present in the liquid. Okay, now if the IMF is strong, it takes a lot of energy to free the molecules from the liquid phase, and therefore the heat of vaporization will be high. So that's why it is easier to vaporize acetone than water at a given temperature, because acetone has lower molar heat of vaporization than water. So more acetone escapes into the vapor phase at a given temperature. Okay, so a practical way to demonstrate this is when you're using cuticle remover. If you put acetone in your hands, it will easily dry up, leaving your hands feeling cool, right? It's because the heat of our hands is enough to vaporize acetone. Now, I will introduce you to an equation that describes the linear relationship between temperature and vapor pressure, which is the Clausius-Clapeyron equation. So I'm not sure with how you pronounce it, but it is used to find heat of vaporization. So the logarithm of the vapor pressure is proportional to the molar heat of vaporization. So we will have this formula. Okay, the natural logarithm of P2 over P1 is equal to the negative molar heat of vaporization over R, which is a constant, multiplied to the difference of 1 over T2 minus 1 over T1. Okay, so some books, they might use this. This will give you the same answer, but the only difference is that here it's P1 over P2 and you don't have the negative sign. So I will leave further discussion of this topic to your higher chemistry, as well as the solving part. Okay, now let's go to the next property, which is the boiling point. We have talked about this a lot of times, but what exactly is a boiling point? The boiling point of a liquid is the temperature at which the liquid converts into a gas. Okay, so that's the baby definition or the simplest definition of boiling point. However, you have to remember that a liquid only boils when its vapor pressure equals the pressure acting on the surface of the liquid. Therefore, we define boiling point as the temperature at which the vapor pressure of a liquid is equal to the external pressure. Okay, we have this thing called the normal boiling point. The normal boiling point is the temperature at which the liquid converts to a gas when the external pressure is 1 atmosphere. So the normal boiling point of water is 100. So the boiling point of liquid depends on the external pressure. We have some books call it the abnormal boiling point. Okay, so for example, at 1 atmosphere, water boils at 100 degrees. But if the pressure is reduced to zero point 0.5 atmospheres, water boils at only 82 degrees Celsius. So that's the not normal boiling point. Remember that this boiling point is related to the molar heat of vaporization. So the higher the molar heat of vaporization, the higher the boiling point, as shown in this table. As you can see, argon has a boiling point of negative 186 and the molar heat of vaporization is 6.3. Okay, and mercury here has 357 degrees Celsius as its boiling point, and the molar heat of vaporization is 59 kilojoules per mole. Okay, so the boiling points of substances reflect the strength of the intermolecular forces operating among the molecules. Okay, so at the boiling point, enough energy must be supplied to overcome the attractive forces among molecules before they can enter the vapor phase. Okay, boiling point is actually one of the unique properties of water. So despite being a small molecule, it has high boiling point. Now, what are the other properties of water? Water is an essential substance to life. It is the most abundant compound on Earth and comprises about more than 60% of the human body. But it is also one of the most unusual substances on Earth. First, because water has a low molecular mass, but it is liquid at room temperature. This is because of the hydrogen bonds which hold water molecules together for small fractions of a second. So the highly polar nature of the OH bond combined with water's bent shape makes water have a significant dipole moment. So one water molecule can hydrogen bond with up to four others, resulting in unusually high boiling point for such a small molecule, which I have presented in the last video. Okay, so next, water is a good solvent. It is referred to as the universal solvent. But what makes water a good solvent? It's the polarity and hydrogen bonding ability of water. Okay, so water dissolves many organic substances that are capable of forming hydrogen bonds with water. Exceptions are the hydrocarbons. Water dissolves salts and other ionic compounds too. They also dissolve gases like oxygen and carbon dioxide. Okay, so oxygen and carbon dioxide will dissolve in water, meaning some animals do not need to breathe air in order to respire, but they must still be able to absorb oxygen and excrete carbon dioxide. In relation to the role of water in plant nutrition, plants are able to absorb nutrient ions dissolved in water. Water can be drawn by plants from soil because of capillary action. These are other unique properties of water. Water has high surface tension and high capillarity. Okay? Next, water has high specific heat capacity. Specific heat is the amount of heat or energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay, so the specific heat of water is 1 calorie per gram degree Celsius. Okay, it is one of the highest for many liquids. Despite that, water can absorb a large amount of heat even if its temperature rises only slightly. To raise the temperature of water, the IMF hydrogen bonds should break. Okay, so the opposite is also true. Water can give off much heat with only a slight decrease in its temperature. Okay, so this allows bodies of water, large bodies of water, to help moderate the temperature on Earth. Okay, so in summer months, this means that water must absorb a great deal of energy in the form of heat from the sun in order for the temperature to increase. Since most bodies of water are large enough not to be significantly affected by the heat from the sun, water provides almost constant temperature for plants and animals living there. It takes about 4.5 times greater amount of energy to heat up water than an equal amount of land. Hence, large bodies of water heat up and cool down more slowly than adjacent land masses. Next, solid is less dense and floats on liquid water. So, unlike all other liquids, the molecules in solid water are actually farther apart than they are in liquid. Okay, so water's hydrogen bonds fix solid water in an open hexagonal structure like this, which is less dense than liquid water. Hence, ice floats on water. When a lake freezes, the layer of ice that forms at the top of the lake insulates the water below it, often preventing it from freezing solid. Okay, so what is the application of all of these properties to aquatic life? So as the lake cools to this temperature in winter, the surface water will sink through convection and warmer water rise up to the surface in a continuous cycle. With that, the dissolved nutrients and minerals present in the warmer water goes to the surface where surface-dwelling organisms can use them. Also remember that water bodies freeze from top down. So if ice is not able to float, the water bodies would freeze from top to bottom and aquatic life will be killed. Because ice floats, aquatic organisms survive under the surface, which remain liquids. The ice surface also acts as an insulating layer, protecting the water beneath from further freezing and maintains a temperature adequate for survival. Without this feature, there would be no aquatic life in temperate and polar regions.